Good afternoon, everyone. Welcome to our ACEAS seminar series. I hope everyone had a good break. First, I would like to start with the acknowledgement of countries. So on behalf of the University of Tasmania, I acknowledge all countries participating in this meeting. I also acknowledge their elders, ancestors, and their legacy to us. I'm very pleased to introduce our speaker today, Dr. Yuhao Dai. Yuhao is a research associate with ACEAS. He's a paleoclimatologist. Yuhao graduated from the Peking University in China in 2013. Then he moved to Canberra, where he got his PhD degree from ANU in 2018. Then he did a few-year postdoc in Europe and Norway, and then finally came back to ANU to Canberra, where he is now. So Yuhao, welcome and thank you very much for this presentation. I think you can just go ahead and share your screen.
Okay. For some reason, I cannot share my screen. It says screen sharing has failed to start. Let me try.
Maybe try again. Maybe you can email your presentation to me real quick, the PDF or something, and I can share from my screen. Oh yeah, it works now. Yep. Please go ahead.
Okay, can you see my screen correctly?
Yes, it's all good. Yep.
Okay, thank you so much for the introduction. Today I'm going to talk about Southern Ocean's role in regulating atmospheric PCO2 during the geological past. So far, I have been trying to understand ocean carbon cycle changes in the past. So to achieve this, I have been analyzed chemical compositions of marine microfossils. This includes trace elements and isotopes. So for example, here is a photo of the microfossils I worked on. They include foraminifera, radiaria, also sponge spicules. So today, I'm not going to talk about these two guys. I will be focused on work based on foraminifera. So here is the Antarctic temperature record and atmospheric PCO2 record for the last 800,000 years. So one of the central questions for paleoceanographers is to understand what is driving this CO2 variability on the glacial interglacial timescale, which is about 100,000 years. So we can see that first of all, these two records correlate with each other very well. And for the CO2 record, you can see that over these last 800,000 years, the variability is almost within the magic number of 180 and 280. So what is driving these atmospheric CO2 changes? So after decades of research, paleoceanographers has come to the consensus that the Southern Ocean processes are very important in driving this atmospheric PCO2 variability. This is because the deep water upwelled in the Southern Ocean is rich in carbon. So in this talk, I'm going to, first of all, introduce the proxies I'm going to use. And I will spend most of the time talking about CO2 outgassing from the Southern Ocean during the last deglaciation, which is 18 to 11,000 years ago. So I will be talking about processes in two regions. First of all, in the subantarctic zone. And secondly, I will talk about changes in the polar Antarctic zone. These two parts will be related to the upper cell and the lower cell of the Southern Ocean overturning circulation. So in the end, I will also provide a preview of the work I'm going to do within the ACEAS, which is about Southern Ocean carbon cycles during the Miocene. Okay, let's start with the proxies. Many of you may not know what exactly a proxy is. So the paleoclimate proxies are physical, chemical, and biological signatures of materials preserved within the geological record. So what we as paleoceanographers do is to calibrate these records to climate and environmental parameters in the modern world. Then with some assumptions, we can use these proxies to reconstruct changes in the past. So in this talk, I will be mainly use geochemistry of foraminifera in marine sediment to reconstruct past seawater biogeochemistry. I'm going to go through all the proxy I'll be using. I will dwell on the first one a little bit longer. So the first one is to use boron isotope in foraminifera to reconstruct seawater PCO2. What you can see here are some calibration curves. What we do is to measure boron isotope in the foraminifera and use these calibrations to derive in this case to derive the boron isotope or borate. From there, with some assumptions, we can calculate the seawater PCO2. Again, here is the ice core CO2 record, PCO2 record in red. These blue dots are reconstruction based on boron isotopes. You can see these two match relatively reasonably well during the last 800,000 years. For the rest of the proxies, I will go through quite quickly. So I'm going to use a magnesium calcium ratio in foraminifera to reconstruct sea surface temperature based on this calibration. And also the nitrogen isotope in foraminifera to reconstruct nutrient utilization efficiency. This is also based on the correlation between the nitrogen isotope in foraminifera bound organic matter and nitrogen isotope of subsurface nitrate. For the deep water reconstruction, I will be using boron to calcium ratio in foraminifera to reconstruct deep water carbonate ion, cadmium calcium ratio in foraminifera to reconstruct phosphate concentration, and I will be using the offset between two basic foraminifera to reconstruct oxygen concentration. Okay, let's start to look at the first part, the first main part of the talk, which is about the CO2 outgassing from the subantarctic zone. So here is a very simplified version of the global overturning circulation, which also show the dissolved inorganic carbon concentration of the water. If we look at the upper cell of the circulation, we can see that upwelling of deep water in the Southern Ocean and the formation of mold water and intermediate waters. So before the formation of this intermediate and mold water, this water with high DIC concentrations will be exposed to the atmosphere and potentially release CO2 to the atmosphere. So this is what we think the global circulation looked like during the last glacial maximum. As we can see here, the circulation are much weaker, shown by these much thinner arrows. So if we look at the subantarctic zone, we see that we think that at this time there were more dust deposit in this region. This can increase the nutrient utilization and cause less CO2 outgassing from the region. So what is the evidence for this argument? Let's look at this record from ODP site 1090 in the subantarctic zone. So on the top, we have the atmospheric PCO2 record for the last 800,000 years. At the bottom, we have the subantarctic zone ion fertilization proxy, as well as productivity proxy at this core. We can see that during the glaciation in the last 100,000 years, there is generally increase in ion fertilization at this core. And during the deglaciation, there is generally a decrease in ion fertilization. So this is also seen. This is also seen in the productivity at this core. So during the glaciation, we generally have this decrease in atmospheric PCO2. So this also argue that this is partly driven by the stronger ion fertilization. Now, if we look at all these 8 glacial interglacial cycles, similar structures can be seen repeatedly. So this has been used to argue for the contribution of subantarctic zone to the glacial deglacial atmospheric PCO2 change. So now, if we zoom into the last 160,000 years, here we still have the subantarctic zone ion fertilization. So on top of this record, we have a record of nitrogen isotope, which show you the nutrient utilization at this site. So what we can see here is that during periods with relatively high ion input, you have more efficient utilization of nutrients. So these processes are thought to be able to control surface seawater PCO2. So during this period with stronger ion fertilization, it's expected that the surface water PCO2 can be lowered. So if you still remember, we have some tools to actually reconstruct surface water PCO2. So now let's look at the last 20,000 years. So this is again the nutrient utilization at this site. So if we think when the nutrient utilization is more efficient, the surface water PCO2 will be lower, you would expect sea surface PCO2 at this site to increase from the glacial period to the interglacial period. But this is not the case for the actual reconstruction. So what is the reason for this? This is because seawater PCO2 is not only driven by nutrient utilization. Mechanisms for subantarctic zones contribution need to be better understood. Actually, from the textbook, we know that seawater PCO2 is controlled by many different factors, including dissolving organic carbon, alkalinity, temperature, salinity. So the first 2 parameters, they are related to the chemistry of the seawater, and they can be largely summarized as a biological pump. So if we have a parcel of water with PCO2 at this level, if we want to decrease the PCO2 of this parcel of water, what we can do is reduce the amount of carbon in this part of water. But we know that solubility of CO2 in seawater changes with temperature and salinity. To achieve the same goal of reducing PCO2 by 40 ppm, what we can also do is to decrease temperature by 3 degrees in this case. So modern oceanographers has been using this method to understand what is going on in the modern ocean. Here is data from North Atlantic with seawater PCO2 in filled circles, as well as surface temperature in empty circles. Because this is modern observations, we can use all different parameters to recalculate these PCO2 values. So what this also did at first is to derive this curve shown by these filled circles. What they did is fairly simple. They keep the DRC alkalinity and salinity and everything else the same. They only considered variability of temperature in this calculation. So this variability here, this variability of PCO2 here can be therefore attributed to temperature, and therefore the solubility of seawater of CO2 in seawater. What you can also do is to ignore the variability of temperature and also only consider variability in DIC. So this is what you can get. This curve with empty circles is what you can get. And the variability here is purely driven by the DIC, or in another word, the biological component. So we can actually use this with a lot of observations in the modern ocean. We can actually apply this method to the Southern Ocean. Here on the top, you have the seasonal PCO2 amplitude in the Southern Ocean. So these two, within these two curves, is the subantarctic zone. So using the same method, you can derive the biological component of this seasonal variability as well as a solubility component. So overall, in the subantarctic zone, the seasonal variability of surface water PCO2 is relatively small in total. But this is not the case for biological pump and biological and solubility components. And we can see here, for example, during summer months, the biology tend to decrease the PCO2, but this is largely offset by the lower solubility driven by high temperature at that time. And we can also see what other parameters, what the variability of other parameters look like. So as we can see here, this biological component has a very similar structure to the variability of DIC, and the solubility component has a very similar structure to temperature. So the other component, such as alkalinity and the salinity, doesn't really has much contribution to these components. And that's good for a paleoceanographer, because these two are very, very difficult to reconstruct. So to summarize, what I want to do here is to use the method that has been used by modern oceanographers to understand what has been changing in the past. So if we remember, we have proxies to reconstruct seawater PCO2 as well as sea surface temperature. So with these two, we can actually calculate how much of the seawater PCO2 change is driven by solubility change. And with the solubility related component and the total in situ change, we can derive the biology related PCO2 change. To verify this biology related PCO2 change, we can compare this to the nutrient utilization efficiency at the site, which can be achieved by another proxy. Okay, here is what we have done. So our reconstruction is from a sediment core south of Tasmania. So we reconstructed surface seawater temperature, surface seawater PCO2, as well as nitrogen isotopes. These are all based on the same foraminiferous species here, shown here. So here are the results. On the top is the temperature reconstruction during the last 20,000 years. On the second row is measured boron isotope, which can be translated to borate boron isotope. Based on this, we can calculate seawater PCO2, and we compare this to the atmospheric PCO2 recorded in ice core. So what I want to do is to partitioning this observed PCO2 change to solubility and biology related component. So first of all, I changed the absolute estimation to the relative change, and with the information of temperature, we can calculate the PCO2 change purely driven by temperature as well as salinity. The difference between the total in situ change and the solubility driven change would give you the PCO2 change driven by biological pump. And if we compare this biology related component to the nitrogen isotope from the same material, you can see that these two have very similar structures, and therefore confirming our method is reliable. If we look at the change from the last glacial maximum to the early Holocene, you can see that the solubility contributed to about 20 ppm of PCO2 change at this site. The biology component contribute to -20 to 40 ppm during this period. So the negative contribution here actually suggests that biology component during some part of this deglacial period is actually helping the Southern Ocean to absorb more carbon rather than release carbon to the atmosphere, which is quite different from what we previously thought. Now, if we zoom into the last deglaciation, we can find that during the period of 18 to 15,000 years ago, the increase in PCO2 change is relatively dominated by the change in the solubility component, and the net change in biology related component is quite small. So this result is actually quite surprising to us. So what we did is to go back to the literature and look at what the published data look like. So we look at all the published sites in the subantarctic zone so far. So here is the result from our core. So on the top, you have the reconstructed PCO2 against the atmospheric PCO2. On the second row, you will have the solubility relative PCO2 change, and at the bottom is the biology related PCO2 change. If we look at data from all these sites, there are some consistent results. For example, the solubility pump consistently contribute to this deglacial seawater PCO2 increase by about 20 to 50 ppm. And at these sites, the contribution of biology to this PCO2 increase is quite modest. Again, we use the same method to reanalyze some of the published model simulation. In this case, we choose to reanalyze Laurie's model output from her 2018 paper. So what we did is to compare the model output from the 15,000 years ago to 19,000 years ago. So we can see this relative increase in outgassing from the Southern Ocean. But if we separate this to the biology and the solubility component, we can see that the biology's contribution is relatively modest in most of the region, but this observed PCO2 increase is largely driven by the solubility change. So putting all this together, we can show that the solubility pump actually played a very important role in modulate past surface water PCO2 change in the subantarctic zone. And as a result of that, we think that the biology's effect to the deglacial subantarctic zone sea surface PCO2 change is less important than we previously thought. Okay, now we can move on to the polar Antarctic zone. Again, we will start from this diagram for overturning circulation. If we look at the Antarctic zone, we can see that compared to the modern ocean, the upwelling during LGM is largely reduced. It is expected that this kind of a reduction in deep water upwelling will reduce the amount of CO2 released to the atmosphere. So what is the evidence for this hypothesis? We come back to this study again. So this time we are looking at a site in the Antarctic zone. Again, on the top, you have the atmospheric PCO2 record for the last 800,000 years. Here, we have two records which are related to export production at this site. And this has been interpreted as a proxy for the strength of an Antarctic zone upwelling. So during the glaciation, there is a general reduction in the strength of upwelling in the Antarctic zone. At the same time, you have a decrease in atmospheric PCO2. This is so based on this. This also argue that the reduction in upwelling, Antarctic zone upwelling, contribute to the decrease in atmospheric PCO2. And during the glaciation, you will have strengthened upwelling, which bring more carbon to the surface ocean and the atmosphere, which drives the increase in atmospheric PCO2. However, this is also the case for the last 8 glacial interglacial cycles. However, there is some issues with this kind of study. First of all, this site is actually not in the polar Antarctic zone. And it has been challenging for all the paleoceanographers to get nice record from the polar Antarctic zone. So one way people has been trying to do is to look at deep sea corals. So here is a synthesis of data from a series of research based on deep sea corals. So these authors come to the Drake Passage and collect a bunch of deep sea corals, as we can see here. But what we can already see is that to collect these very spatial samples requires a lot of effort, and the distribution, the geographic distribution of these samples is quite limited. So here are the data from these authors. So in general, these results are consistent with what has been hypothesis. But if we don't look at the details of this record and only look at the temporal distribution of this material, you can see that these records are quite patchy, because as you collect these deep sea corals, you have no idea of their age, and it's very difficult to get a continuous record with decent resolution. And if we come back to this record again, these are excellent results. But after 10 years since its publication, what we really need now is more quantitative understanding of these deep water changes, and we need to find other ways to do this. So my strategy is to use deep ocean records to recalculate what happened at surface in the polar Antarctic zone. So if you may be familiar with this equation. So for any nutrient, in situ nutrient concentration in the deep ocean, it can be decomposed into the preformed and the regenerated components. So the preformed component is what is as its name suggests, what is formed at the surface of the ocean. So it turns out that for phosphate, the preformed phosphate is a very important parameter for the global ocean biogeochemical cycling. So it largely determines the biological contribution to the atmospheric PCO2 drawdown. As shown by these authors, when you decrease the preformed phosphate concentration, the global mean preformed phosphate concentration, you can actually decrease the atmospheric PCO2 quite efficiently. So now let's have a look at what the modern ocean biogeochemistry can tell us. So I'm going to show you a few depth profiles along this section from the North Atlantic to the Southern Ocean, along the Southern Ocean, or come up to the North Pacific again. We are all very familiar with the distribution of phosphate in the ocean, in the global deep ocean. It generally increases from the Atlantic to the Southern Ocean. Then we have the highest values in the Pacific Ocean. So actually, for oxygen, it's in general the opposite. We have relatively a higher oxygen concentration in Atlantic, and we have relatively low oxygen in the Pacific. So these changes in oxygen concentration, they are mostly driven by regeneration of organic materials. So based on the rate of field ratio, that is the ratio of oxygen consumption and phosphate production, you can calculate the regenerated component of phosphate concentration. So based on this equation, we can then work out what the preformed phosphate look like. And now we will take a closer look at the preformed phosphate. So first thing you can see that the global ocean for preformed phosphate, global ocean is largely determined by two n-member mixing from the North Atlantic as well as the Southern Ocean. If we look at the deep Southern Ocean and Pacific, you can see that it is relatively homogeneous. So this suggests that we can use reconstructions from the deep Southern Ocean to work out what the its preformed concentration and use that to infer what happened in the surface polar and Antarctic zone. If you still remember, we have some tools to reconstruct phosphate concentration and oxygen concentration in deep water. Combine these two, we can get the preformed phosphate concentration, which is largely the polar and Antarctic zone changes driven by nutrient utilization. But what we also want is the total amount of CO2 change driven by ACE exchange. How do we get there? We can use this tracer called ACE signature of carbonate ion. So this is a tracer that is mainly driven by ACE exchange at surface. You can with some caveat, you can say it is a preformed concentration of carbonate ion, because in the deep ocean, deep water carbonate ion is negatively correlated to the de-icing concentration. You can use this tracer to work out what is the de-icing change driven by ACE exchange. And how do we calculate this? Actually, phosphate and de-icing are also correlated due to regeneration, organic matter regeneration in the ocean. So if we can have reconstruction of carbonate ion as well as phosphate concentration with assumptions about Rayleigh ratios as well as the export productivity, the Rayleigh ratio of organic carbon and inorganic carbon remineralization, we can calculate this tracer. So here I show you the carbonate ion and the phosphate concentration along the transaction from the North Atlantic to the Southern Ocean and back to the North Pacific. Remember that when we have relatively high carbonate ion, the DRC is low. So if we combine these two, we can derive the ACE exchange component of carbonate ions. So it's striking to see that the carbonate ion AS has a completely different or reversed trend compared to carbonate ion. So why is this? We know that there is more carbon stored in the Pacific compared to Atlantic, but this calculation shows you that this trend is largely driven by remineralization of organic matter rather than ACE exchange. So here in the Pacific, you have relatively higher carbonate ion AS. This means that deep water from the Pacific Ocean or the Southern Ocean has experienced relatively inefficient ACE exchange as opposed to the North Atlantic ventilated deep water. Okay, here with all these deep water proxies, we can derive phosphate, preformed phosphate, as well as carbonate ion AS. So for the carbonate AS, it records all the carbon exchange happened in the polar Antarctic zone. So part of this is driven by biology, but part of this is purely kinetically driven. So ideally, combine these two, we can also assess what is the CO2 exchange related to kinetics look like in the past. And this can, in some way, assessed by radiocarbon of deep water. Okay, now we can come to our reconstruction. So again, these reconstructions are based on the site south of Tasmania. And these are the results. So the first 3 columns show you the reconstruction of in situ concentration of carbonate ion, oxygen, and the phosphate concentration. Combining them with some assumptions about temperature, salinity, etc., we can calculate the preformed phosphate as well as the carbonate ion AS. So this carbonate ion AS give you a direct evidence of the deep Southern Ocean's contribution to carbon loss through ASE exchange, which is a very which cannot be achieved by many of the previous studies. And if we compare this carbonate ion AS record to some other proxy records, we can better understand the mechanisms driven this carbon loss from the deep Southern Ocean. So again, here on the top we have the carbonate AS. We also have the preformed phosphate concentration shown in blue here. So what we can see here is both the record has very similar trends during the last deglaciation period. And what is more, the preformed phosphate concentration at this site is quite similar to the structure of nutrient utilization from records from deep sea corals, as well as some upgrading proxies in the South Atlantic. So combine these records together, we can show that the biological pump played an important part in driven the CO2 outgassing from the polar Antarctic zone during the last glaciation. What we also have here is the radiocarbon at this site, which is a proxy for ventilation, physical ventilation of the deep water. So we can see the general increase in early deglacial ventilation is coincided with the increase in carbonate ion AS, and this radiocarbon record is have a similar structure to the polar sea ice around Antarctic. So combine these records together, we can show that there is also likely a strong kinetic driven component in the ASE exchange in the polar Antarctic zone. So again, what we did here is to compare what we see at our record to some published model simulation. So here we use Loris model again, and here are the Indo-Pacific zone, Indo-Pacific zonal means of 3 different traces between 19,000 years ago to 15,000 years ago. So these positive changes in carbonate iron AS, preformed phosphate, as well as the radiocarbon edges are consistent with what we have seen in our record. So in conclusion, we provide evidence for the carbon loss from deep southern oceans through outgassing in the polar Antarctic zone. And we can show that this outgassing is controlled by both biological and kinetic effects. Okay, here we come to the last part of the talk, and I will give you a very brief introduction to what I'm going to do with ACEAS. That is to look into how the Southern Ocean carbon cycle worked during the Miocene. Why Miocene? I think most of us has read about this paper published by our colleague. So in this, in the concluding paragraph of this paper, they say these changes in the Southern Ocean overturning circulation can profoundly alter the ocean overturning of heat, fresh water, oxygen, carbon, and nutrients. So in general, it is also important for paleoclimate to help understand these changes in a warmer climate, so we can have a better understanding of what this impact that will be felt through the global ocean for the centuries to come would look like. For this reason, we are going to look at changes during the Miocene. So here is the reconstructed atmospheric PCO2 in the last 20 million years, and the time is in log scale here. You can see that, first of all, the current level of atmospheric PCO2 is unprecedented for almost 10 million years. And if we want to get to the projected atmospheric PCO2 level by the end of the century, we really need to go back to the Miocene for the geological record of it. So on the bottom, we have records of benthic oxygen isotope, which is a proxy for deep ocean temperature as well as ice volume, global ice volume. What we also have is the deep ocean temperature here. So overall, the Miocene Ocean is much warmer compared to the modern ocean, and the ice volume at that time is much smaller. So now let's have a closer look at what the Miocene climate looked like. So now the time axis is linear again. So first of all, we believe that there is an AAC. There is an ACC, the Antarctic Circumpolar Current during Miocene, although it is much weaker compared to the present day. And at some point during the Miocene, the northern component water is also established. During the Miocene, we already have permanent ice sheets in the Antarctic, and we have experienced some fluctuation in ice sheets during Miocene as well. These all sounds very familiar, what we probably are going to experience in the next century. but it's also worthwhile to bear in mind that the Miocene is not the perfect analog to the future, because for example, the ocean gateways are quite different compared to the modern world. So what are we going to do? So what we want to do is to reconstruct the distribution of heat, carbon, and nutrients in the Southern Ocean. We also want to look at what is the variability of these properties on the timescale of tens of thousands years. What we want to know is what this diagram would look like for the Miocene. And we will achieve this by investigate 3 sediment cores south of Australia. So by choosing these cores at different depths, we are hoping to capture water masses at different depths. And we will try to use different proxies to reconstruct the nutrient distribution in the Southern Ocean during the Miocene, and see how that may help us understand how the Southern Ocean may operate in a warmer than present world. Thank you for your attention. That's it from me.
Thanks, Yuhao, for the very nice presentation. It was great. There's time for a couple of questions. If anyone has a question, just go ahead and unmute, I think, and ask your question, or put them in the chat. Yeah, Sana.
Hi, Yuhao, that was great. Thank you very much. I had 2 questions, but one is, so in the subantarctic, you found that the biological pump is probably making less of a contribution than I guess we thought. Does that mean that the temperature change was greater than we thought, or like what do you attribute the kind of greater contribution of the change in solubility to? Is it that the temperature has been underestimated?
Yes, I think the general conclusion I want to draw is that temperature is underestimated, but this doesn't mean that there is no significant contribution from the biological pump. For example, if we really look into this record, we can see that the biology recorded at any fixed site is driven not only by the overall change of biological pump in the subantarctic zone, but it is also driven by its relative position as well as the ion fertilization. For example, when you have no change in biological pump observed at this site during the early deglaciation, but if you also bear in mind that during this time the subantarctic zone actually moved to the south, that is, this site is moving away from the center of the region where this ion-related fertilization will impact the productivity. So it actually shows that there is no change in this biology-related CO2 component. Actually imply that there is actually a component of productivity-related PCO2 change, but it's not as dramatic as we previously thought. I think that's the main thing I want to argue.
Thank you.
Yuhao, there is a question in the chat. Can you please have a look at that?
Okay.
Innovation.
No, I'm afraid not. Because so these paleoclimate models, they generally have much closer resolution. I think for this simulation, the resolution is about 3 degrees in latitude, I guess. So it cannot resolve these changes. So yeah, in the ideal world, I really want to see how this process affects carbon cycle, but that's quite far away from a paleo perspective, I would say.
There's a question from Alex. Alex, just go ahead and unmute yourself.
Thanks for the talk. So I guess one of the assumptions for all these studies is that the forams in the core are representative of the conditions above the core site. And how valid is that assumption? If you've got, a lot of ocean circulation is going to be bringing forams from all over the place.
Yes, it's going to be from all over the place, but not so far away, because they have relatively short life cycle, and because they are not that small, they sink relatively quickly. So actually, if you take a sediment trap in the ocean, you can actually see for example, the temperature recorded by these forams correlated to the seasonal variability of seawater temperature quite well. So yeah, that's a problem I have when I started studying paleoceanography, but yeah.
Thanks.
All right, Fabio.
So great talk, Yuhao. I'm having a question that in one of your slides, you showed that the reduction in the upwelling lead to the decrease in the PCO2 also. So this is the I think that was a slide. So is this the outgassing of CO2 from the ocean, or it is the absorption of CO2 into the ocean? Like
the assumption here is definitely the release of CO2 from the deep ocean to the atmosphere, because we think that because the circulation is quite weak, so this export production or the upwelling is more representative of the pure physical CO2 outgassing. Yeah.
So I don't know much about it, but when the CO2 is absorbed into the ocean, then it will convert into might be organic carbon or like the inorganic carbon or something like that. So
yeah, so
how the outgassing makes the CO2 available in the form of gas?
So yeah, I think so the assumption here is that the uptake, so because there is actually, as you can see, there is enhanced productivity during this time period. So actually there is a lot of productivity that is reducing the amount of CO2 from this region, but this cannot keep up with the amount of PCO2 that is directly brought up from the deep ocean. I think that is the process. So the upwelling of CO2, so release of CO2 from upwelling water is a dominant process contributing to this atmospheric PCO2 increase. Yeah.
Thank you.
Okay, well, we have to wrap up now. Well, thanks, Yuhao, again for your presentation. See everyone again in a month for our next seminar. Bye.